Right, here we go with CCEA Unit 2 in Physics, and Unit 2 is Waves, Photons and Astronomy. And this is from 2018. Let's get started. Question 1. A student observes the spectrum emitted by a mercury vapor lamp and notices that each line has a different colour as represented by figure 1.1. Explain the origin of the different colours observed. So what's going on here is that the mercury atom, its electrons are only allowed to be in very specific energy levels within, and so they're not allowed a continuous energy. And so if the electrons are only allowed to be in specific energy levels, then when they jump between those, they'll emit very specific electromagnetic radiation, and each one of these lines corresponds to photons of a specific jump between levels. So you're explaining that there are only specific energy levels and that the electrons will move between those levels, and when you're transitioning, then they will emit photons corresponding to those energy gaps, to the energy gap that they've jumped, and that's why only specific photons are possible. Part B. Figure 1.2 shows some of the energy levels for the hydrogen atom. So we've got energy levels that are labelled A, B, C, D, etc. and we've also got them written in their electron volt values. State the magnitude of the energy level of the ground state of the hydrogen atom shown in figure 1.2. So this is just, do you recognise which one of these is the ground state? And it's the 13.6, the lowest energy. So we just fill that in as minus 13.6 eV. Write down the expression for the wavelength lambda of the radiation emitted during a transition between two energy levels. The two energy levels are separated by an energy difference, delta E. Identify any other symbols used. So what goes on here is that a transition of delta E releases a photon of the same energy. And so Planck's relationship tells us that, that the photon energy can be written as HF, or if you're working with wavelengths, it can be written as HC over lambda. So delta E equals HC over lambda would be our starting point. So lambda would then be HC over delta E. So we have to identify what H and C are, because the other two things are explained in the question. So H is obviously Planck's constant and C is the speed of light. Part 3. Calculate the wavelength of the photons emitted when electrons fall from level D to B in figure 1.2. So let's have a look at that energy level diagram then. So these are the energy levels from that diagram, A, B, C, D. Let's just put some labels on it. And they have asked us specifically to look at a transition between the D and the B levels, so that's a transition down between those two levels. And so we can see the energy level gap there. We're going from minus 0.82 to minus 3.38. So they want a wavelength, and surprise surprise, we've just set up here that lambda is going to be HC over delta E. Always remember that when questions run in little subparts that they're often related to each other. So we're just substituting in there. The only difficulty would be that these energies are electron volts, and that's not SI, and therefore you're not going to get meters out of this equation until you put that delta E in joules. So we need to write the energy gap and convert it to joules first. So delta E is the difference between the two energy levels, which in this case is minus 0.82 minus 3.38. That gives us a delta E of 2.56 electron volts, and then we need to multiply by the electron charge to convert that to joules. So, we could substitute that now without working out how many joules it was. So we put in our Planck's constant and our speed of light and our 2.56 and our electron charge to convert it to joules, and that should give us the lambda we're after. And that gives us a lambda of 4.85 times 10 to the minus 7 meters. So power forces are the photons emitted during the transition from D to B visible? Explain your answer. So firstly, just remind ourselves that 4.85 times 10 to the minus 7 is like 485 nanometers. And we have visible spectrum that runs from 400 to 700 nanometers, so that is definitely within that range. Part C, explain how laser action works. In your explanation, use and describe the terms population inversion, metastable state, and stimulated emission. So we need to explain excitation, I suppose, first. So electrons in the atom of the laser material are excited to higher energies, and they accumulate then in the long-lived metastable state. We then need to explain population inversion, when we've got more in that state than in the ground state. So population inversion occurs when more electrons are in the metastable state than in the ground state. And now we need to explain stimulated emission. So a photon corresponding to the metastable to ground state transition passes other atoms, stimulating their electrons to transition down and emit identical photons. This is stimulated emission. These photons then pass other atoms, creating further stimulated emissions. So we're exciting the electrons, they're accumulating in the metastable state. Population inversion occurs when there's more electrons in the metastable state than in the ground state, and then we get some photon that has been, spontaneously emitted, passing these excited electron atoms, and because it's the identical photon produced by that transition, it's able to create what we call stimulated emission as it passes those atoms. And so we get lots of identical photons, all capable of creating stimulated emission because they're all of the right type. Question 2a, explain the meaning of the term diffraction. Remember, diffraction is where waves pass a gap or obstacle and they spread into the unexpected regions behind the obstacle or gap. Part B. Figure 2.1 shows diagrams of wavefronts as they approach two different sized apertures. Carefully complete the diagrams to show how aperture size affects the diffraction pattern observed for water waves. Okay, so this is your wide gap, narrow gap. Very, very straightforward. When the gap is similar to the wavelength, we'll get more noticeable curvature. I tend to think of this differently. I tend to think that the curvature is always there. It's just that when the wide gap is present, you have a straight bit in the middle. So we'll do the bottom one first. And so we want to make sure that we keep the wavelength the same. So you're trying to make these curved and not mess with the wavelength. And I haven't done that very well, but you get the idea. So with this other one, you imagine that the sides will have this bit, and the other side will have this bit, and then there'll just be a straight bit between them. So I'll see if I can show you what I mean. So we still have this curve, and we still have this curve, and we still have this curve. Try not to make the wavelengths different. So we still have that curve, still have that curve, and we still have that curve, but there's a straight bit in the middle. And that's the way I tend to always think of these diagrams, is that the edge curves are still there, but there's the opening of the gap creates a straight bit in the middle. So the trick here is to keep your wavelength the same and make sure that the wide gap has straight bits in the middle. Part C, light from a laser is incident normally on a diffraction grating with 200 lines per millimeter. Figure 2.2 shows a schematic diagram of the apparatus and the observed pattern on the screen. The distance along the screen between both the third order maxima was measured to be 60.6 centimeters. The distance between the diffraction grating and the screen is 84.2 centimeters. So you can see the layout there with the dimensions marked on the picture. Use this information to show that the angle of diffraction for the third order maximum was 20 degrees. So obviously we've got a bit of trig here to do. So we need to take a fraction of that width between the 0 and the third order and try and demonstrate that that angle there is 20 degrees. So half of the width is 30.3 and the distance up to the screen is 84.2. So we're just doing like the tan of theta. And I'm getting 19.79 for that, which is approximately 20 degrees. Part 2, calculate the wavelength of the laser light used in this experiment in nanometers. So obviously the third order angle will be usable then to figure out the lambda in the equation. So we've got the equation that says that d sine theta is equal to n lambda, standard diffraction grating equation. So we need to work out our grating spacing based on what they told us, and what they did tell us was that in 1 millimeter there were 200 lines, and that gives us like 5 times 10 to the minus 6 of a meter for D. And n equals 3 because it's the third order. Always a good idea to rearrange your equation before you start substituting, so I would rearrange it as lambda is d sine theta over n before I start. And this is where the issue crops up of which theta do you use? Do you use the 19.8 that you calculated, or do you use the 20 degrees that they told us? And usually the mark scheme will be set up so that you can use either. The other advantage of that is that if you couldn't get part 1, you still know that the angle is 20 degrees and therefore it can be used in this part. So we'll use the 19.8. So D was 5 times 10 to the minus 6. You should always talk your way through calculations to make sure you've substituted correctly. 5 times 10 to the minus 6. We got that from over here. Sine of the correct angle, yeah, and n was 3 because we were talking about the third order. And that gives us a lambda of 5.65 times 10 to the minus 7 meters, or 565 nanometers. Electrons of mass m and charge E are emitted at a hot cathode. They are accelerated to a speed v by applying a potential difference v between the hot cathode and the anode, and the arrangement is shown in figure 3.1. The speed of the electrons can be given by the expression that v equals k times the root of v, where k is a constant. Find an expression for k in terms of E and m. So what you've got here is an electron being released here, and then this voltage acts on it, and so you've got work done there. If you think about the electrical properties, you've got work done which is equal to the charge times the voltage it's crossing. So that'll be the work done on this electron. Now, the charge on an electron is called little e because we're told that here. So Q becomes little e, and the voltage just stays as V. So the work done on an electron like this is little e times the voltage. And that's what gives it its kinetic energy. So that'll be equal to a half mv squared, where little m represents the mass of the electron and v squared represents its velocity. So that's your starting point there, that EV will equal half mv squared. So you're just using the W equals QV, the electricity equation, only in a different context here, that the work done when a charge crosses the voltage is Q times V. And so if the Q here, the charge on this particle, is little e, then E times V is the work done, and that will give it its kinetic energy. So that's all you're saying, that the work done equals the gain of kinetic. And then you just rearrange that to get V on its own, and you should be able to see what K is. So to get rid of the half, we're going to need to multiply both sides by 2. To get rid of the m, we're going to need to divide both sides by m, and then to get rid of the squared on the v, we'll need to take the square root. So 2 times EV over m, and then the square root of that is going to be a value for v. And then you just get the root of v on its own. And so k must be what's in that first root there. We can represent the original root as the product of two roots. So the root 2e over m must be k by inspection. So k must be the root of 2e over m. The moving electrons each have a kinetic energy of 1.55 times 10 to the minus 15 joules. Calculate the momentum of these moving electrons. Well, momentum P equals mv, and we just said that v was the root of 2 times e times v over m. And since they've given us this figure, we could remind ourselves that that also equals EV. So we could write this as V equals the root of 2 times the kinetic energy over M. So if P equals M times V and V equals this root, then P equals M times this root. Now there are two schools of thought here. There's one school of thought that says I should work out V and just stick it in with the M. But there's another school of thought that says you write an expression and then you substitute once very carefully, and that way you've only got one place where you can make a mistake rather than multiple places where you can make a mistake. So I prefer to write out the full expression for what I'm trying to find and substitute once. And the top mathematicians will realize that there was something I could have done there to simplify that and avoid having to write the mass of the electron in twice, but I've avoided that just not to make this too mathematically challenging. So we substitute into all of those and we should get a momentum in kilogram meter per second, and that gives us 5.31 times 10 to the minus 23 kilogram meter per second. Part 2, calculate the de Broglie wavelength of these moving electrons. So remember, we have the de Broglie wavelength that lambda is h over p, h over the momentum. And so we just substitute in Planck's constant and our momentum from the previous part. And that gives us 1.25 times 10 to the minus 11 meters. Part C, in an electron diffraction tube, fast-moving electrons pass through a very thin metal foil target before striking a fluorescent screen. The arrangement is shown in figure 3.2, and you can see there you've got your standard evacuated container, glass tube usually. You've got a source of electrons here producing an electron beam, so there's some kind of electron gun here with a filament and an accelerating voltage. You've got an electron beam that then is allowed to hit a metal foil, and then these electrons will come out in various angles here, and you need a fluorescent screen so that when they strike it, it lights up and shows you where they've gone. Sketch in the space below the diffraction pattern obtained using the electron diffraction tube apparatus. So you should end up with a set of concentric circles in this experiment, as best as you can draw that. So these are the diffraction orders. So you imagine, like, if you take any straight line through this, you would get your standard laser diffraction grating, but what happens in the electron diffraction is they're going through a grid of materials, so you've got like multiple direction diffraction gratings, and so you get circles instead of dots in a line. Part 2, state how the pattern changes when the accelerating voltage is increased. So remember that lambda is h over p, and if you increase the accelerating voltage, the electrons will go faster, so p will increase and lambda will go down. So increasing the voltage makes lambda go down. So you have to ask yourself what would happen here if lambda was smaller. Well, if the gap stays the same and lambda gets smaller, then the diffraction will move in, the orders will come in. So the electrons will be less strongly diffracted if their lambda is going down and the gap separation in the crystal stays the same. So we would expect the pattern to decrease in size for the rings to shrink in. So the radius of each order will decrease, and so the circles will get smaller. Question 4 shows a loudspeaker placed over the open end of a cylinder of length 1.2 meters. The loudspeaker is connected to a signal generator which can be used to vary the frequency. Describe how you would use this apparatus to obtain the first mode of vibration of a standing wave in the air column. Okay, so if you're trying to find the first mode, you have to start with the signal generator set to its lowest frequency. And then you slowly increase that until you hear a resonant loud sound. So something like this, start at the lowest frequency and slowly increase the frequency until the sound grows suddenly louder. Fine tune the frequency to find the strongest resonance or loudest sound. So it'll grow louder and then you adjust to make it as loud as possible. And that's your first mode. You must start at the 0. If you don't start at the 0, you could miss the first mode and find some other mode. So you must start at the 0. And then when it goes loud, you adjust until you can make it the loudest you can perceive. And that's you set. Part 2. On figure 4.1, sketch the standing wave pattern formed in the tube in this mode of vibration. Mark the positions of all nodes and all antinodes. Okay, so remember an open-ended tube has an antinode at the open end and a node at the closed end. So there's a reflection there. So in theory, the first mode of vibration is just a quarter of a wave. So if we just move this down so we can see, then we're interested in drawing a quarter of a wave with a node at the bottom. And that looks like that. So we've got a node down here, and we've got an antinode here, and that is the fundamental. Part B, 1. The first mode of vibration, or at the first mode of vibration, the frequency reading on the signal generator is 70.0 Hz. What is the value of the speed of sound that can be obtained from this result? So the length of the tube is 1.2 meters. The frequency is 70 Hz. We need to remember that L is lambda over 4, and therefore lambda itself equals 4L, which would be 4.8 meters. And then we can do V equals F lambda on that. And that gives us 336 meters per second. Part 2. Determine the values of frequency F1 and F2 at which the next two modes of vibration occur. So this is the next position where a resonance can occur with an antinode at the open end and a node at the closed end. So you can see that this is like 3/4 of lambda. So the original one's like lambda over 4, this is like 3 lambda over 4. So this is going to be 3 times the original frequency. And you realize again, if we were to keep going with that and draw the next position, it would be at like 5 lambda over 4. So these are going to occur at odd numbers. So F1 is going to occur at 3 times the frequency, and F2 is going to occur at 5 times the frequency. And so that's going to give us frequencies of 210 and 350. Okay, part C. Water is now added to the cylinder until it is 1/4 full. The signal generator is switched on, and it is noticed that the first mode of vibration is no longer at 70 Hz. Calculate by how much the reading on the signal generator must be changed to observe the first mode of vibration. Okay, so it's a quarter full. We need to think about how deep it is. So if it's a quarter full and it's normally 1.2 meters, then the open space must be at 0.9 meters, 3/4 of that. So our quarter wavelength is now 0.9 meters. Means that lambda is going to be 4 times 0.9. So lambda is 3.6 meters then. And f is going to be v over lambda. And we had a speed of sound from the first part of 336. We just put in our lambda now to get a frequency. And so that's our new frequency. That's not the answer. They want the change in the frequency, and that's going to be how much we had to change it from what it was before. So the change is going to be 93 minus 70, which is 23 Hertz. Question 5. An observer sitting on a platform at a train station listens to the sound produced by a train moving through the station at a constant speed. Discuss the changes in the observed sound, including your discussion, the frequency of the sound as the train moves towards and away from the observer, the Doppler equations to describe the frequency or wavelength of the sound as the train moves towards and away from the observer. Include an explanation of any symbols used. Okay, so we need to do the frequency and the towards and away. Okay, to try to use words, if frequency is a number, okay, that number will increase, decrease, or stay the same. So it's important to think in those terms, that when they ask you to talk about the change of some particular parameter, if that parameter has a number, then you're looking to use increase, decrease, or stays the same, rather than up, down, bigger, higher. Be careful about using those words. So towards, if it's coming towards us, the frequency will be increased, and then we do away and frequency will decrease. And the second part, to describe specifically the Doppler equations relating to the frequency or wavelength of the sound as the train moves towards or away from us. Right, so normally lambda just equals v over f, where v is the velocity of the sound. But in the case of the Doppler equations, the lambda for moving away is modified by the movement of the train. So it's still a v over f, but we add in the movement of the train to make that lambda longer. And in the towards case, we subtract off the movement of the train in order to make that lambda go shorter. So my best advice here is to think of it in terms of, there's a basic lambda, which is v over f, but in these two motion cases, it's modified by what's going on with the movement of the train. Now, if you remember that when something moves away from you, wavelengths get longer, then you'll know to add the velocity of the train in that equation and to subtract it in the other one. And that's really the trick to doing this and getting those equations right. Part B, 1. When astronomers observe distant galaxies, they notice that the light is red-shifted. What is redshift, and how do astronomers explain the redshift observed in light from distant galaxies? So remember, redshift is spectral lines belonging to stars appearing further towards the red end of the spectrum than where they should be. And the explanation is that those galaxies are receding, moving away from us. Part 2 then, the shift in wavelength of light from a distant galaxy is 2.2 times 10 to the minus 9 meters. The wavelength of the light observed is 550 times 10 to the minus 9 meters. Calculate the recession speed of this galaxy in kilometers per second. So what they're giving us there is the things that appear in our equations. They're giving us a delta lambda and observed lambda. Okay, so that's not exactly lambda. That's the new lambda rather than the original lambda. So we need to think about what the original lambda is. So it's not quite the correct lambda because it's the observed light. So we need to get the correct lambda out of that. Now, I've just looked at the mark scheme and it doesn't mention any of this. So they've just gone ahead and used the 550. But I'm suggesting that if this is the observed light, then its wavelength has been made longer by this shift value. So it's again one of these things. Are they telling us that this is the proper wavelength, or are they telling us that this is the shifted wavelength? And so, yeah, you're into the what do they mean. Sometimes CCEA aren't really clear with what they mean. So if they said observed in the laboratory, or a similar line observed in the laboratory, then 550 is the right answer for lambda. But otherwise, our delta lambda over lambda, the lambda on the bottom line needs to be the correct non-moving observed wavelength. And I think this is the shifted wavelength. So in theory, the correct wavelength would be 2.2 less than 550. But we'll go ahead with what the mark scheme says. So delta lambda over lambda is V over C, which means that the recession speed, V, is going to be delta lambda times C over lambda. And so we just substitute in there. And again, you might look at this and say, well, why am I putting in 2.2 and 550? Well, they're both in times 10 to the minus 9 meters, so if you include that, they would cancel anyway. So remember that this ratio of delta lambda over lambda has no units, and therefore it's just a ratio. What happens in this is that the unit comes back in as the unit of C. So the unit returns to the thing. 2.2 over 550 doesn't have units, but the 3 times 10 to the 8 does. And so you can leave the delta lambda and lambda in pretty much any unit, as long as it's the same unit, and this should not be a problem. Difficulty here is that this will come out in meters per second, so just be careful. So yeah, for kilometers per second we need to knock those last 3 zeros off. Part C then, calculate a value for the estimated age of the universe in years. And so with no other numbers here, they're obviously going to ask us to do 1 over the Hubble constant. So this is a very rough approximation using the SI version of the Hubble constant, which is 2.4 times 10 to the minus 18 seconds to the minus 1. And taking 1 over that gives us 4.2 times 10 to the 17 seconds. And if you divide that by 60 times 60 times 24 times 365, you should get it in years. And that gives us an age of the universe of about 1.3 times 10 to the 10 years. Describe an experiment to obtain results needed to draw a graph from which an accurate value for the focal length of a converging lens can be determined. In the space below, draw a labelled sketch of the apparatus you would use. Clearly identify on the diagram the measurements to be taken. Okay, so firstly, it says very clearly that whatever we're going to do will involve the drawing of a graph. And we're trying to find an accurate value for the focal length. So we need to work with U's and V's. So we need some kind of identifiable light source, something with a shape on it that we can focus. We need our converging lens, we need a screen, and we need to be measuring the U and the V values. So in this experiment you have to have some kind of illuminated object, so something that has a shape that the lens can be used to focus onto this screen. So a lot of the characteristics here of what you can say below can be clarified in what you draw. Okay, so few basic things. One, you should really mention that whatever you get here should be a sharp image when you're making these measurements, because lots of people forget that. Secondly, you should be very clear that U is from the position of the illuminated object, not just some vague locale here, but very specifically right to where the illuminated object is, right to the center of the lens. And the same for V, center of the lens, right to the location of the sharp image. So be very, very clear what it is you're measuring, and when you measure them when you've got that sharp image. You don't measure them at any other time. You should also mention any instrument that you might need. So your meter rule or meter stick is part of the apparatus for this experiment, so you'll definitely need to mention it there. So you could put in that the lens is in a holder or something, but the position of the lens is more important than how it happens to be there. So that should probably be enough drawing. So now you have to outline a basic procedure, and obviously what you do is you make adjustments to the object distance by moving the screen, by moving the lens, and then you adjust the image distance by moving the screen until you obtain a sharp image, and then you repeat that for various combinations of U and V. So your standard explain in detail how to make the measurement once, and then explain that you have to take a range of different values. Okay, so label both axes and sketch a line graph which can be used to determine an accurate value for the focal length of the lens. So we have U and V values, and the best way to do this is to think about the lens equation. So if we are going to plot 1 over U and 1 over V, then you'll get something like that. And since this is like in the form of y equals mx plus c, we're going to get something with a negative gradient when we do this. So you're going to get a graph like that. So it's these two intercepts that are of interest, because when this is 0, then this equals this, and when this is 0, then these two are equal. So both of these intercepts are 1 over f. Question 7. A diverging lens can be used to produce an image of a real object. Draw a ray diagram for the diverging lens in figure 7.1 to locate the image of the object O. Label the image I. Show where the eye should be positioned to view the image. Okay, so the first thing we do is put a ray parallel to the axis going towards the lens. Okay, now that ray will diverge as it leaves here, as if it's coming from the focal point here. So we've got this turning and doing this. We also need a ray running through the optical center, which will pass straight through without changing direction. And now we need to dot this ray back until these meet back here. So remember, what's going on here is these rays are diverging, they'll never meet again, but this is where an eye thinks this one is coming from, and so there's a common point back here where they both appear to be coming from, and that's where the image is. And that, as they say, is that. We do have to put an eye on because virtual images can only be seen by looking through the system, and we need to look through where the rays are emerging. Okay. So describe the image by placing ticks in the appropriate boxes in table 7.1. Well, it's a virtual image, it's definitely diminished, and it's definitely upright. So that's easy once you've drawn the diagram correctly. Part B, an object is placed in front of a diverging lens of focal length 15 centimeters. The height of the object is 14 centimeters, and the linear magnification of the image is 0.42. Calculate the distance of the object from the lens and the height of the image formed. So we have a diverging lens, which means that the focal length is negative. They've also given us the magnification value, which equals the height of the image over the height of the object, and v over u. Height of the object is 14 centimeters, so we could immediately calculate the height of the image using the magnification. So that gives us an image height of 5.9 centimeters, sticking to the two significant figures. So now we have to try and use the lens equation to get the object distance. Now, we don't have an image distance. What we do know is that v over u is 0.42, so we can express one in terms of the other. V could equal 0.42 u in our equation. So substituting into this, we need to be very careful. It's a diverging lens, so f goes in as negative, but v, the image distance, will be virtual, so it also has to go in as negative. So we've got something like this, with v going in as 0.42 u, but negative, f going in as minus 15. So if we take a common denominator, 0.42 u, then we'll get minus 1 plus 0.42 over 0.42 u, and that'll be equal to the minus 1 over 15, or 1 over minus 15 if you want to call it that. So that top line simplifies to 0.58, negative of that, and then we need to cross multiply by the 0.42, so we get 0.42u over minus 15. We now need to multiply these two negative numbers and then divide by the 0.42, and that gives us a u of 20.714, which we'll put down as 20.7. And with the magic of the iPad, you can't see the 2 times I made a mistake in that fraction calculation. But there we go. I had this term wrong twice. But that's the magic of the iPad. You'll never know that. 8a, Part 1. Waves may be categorized as either transverse or longitudinal. Describe in terms of particle movement how to distinguish between these two categories. So in a transverse wave, the particles vibrate perpendicular to wave propagation direction, and in the longitudinal, they vibrate parallel. Explain what is meant by polarization and state which category of waves can be polarized. Okay, so you should have a simple sentence learnt for this. Polarization is where the vibration direction is confined to the same plane, and this can only happen in transverse waves. So these two questions are like classic examples of stuff that's straight out of your notes. So you should have these things written down in a simple version for putting into exams. If it's simple and can be learnt off, then that's really what you should do. You shouldn't be winging this on the day and risking losing one of these marks. Part B, a student writes the equation for the period t of a wave as shown in equation 8.1, where lambda is the wavelength and v is the wave speed. Show that equation 8.1 is valid. So this is like you to think about your relationship between frequency and period. So reminding yourself that t is the same as 1 over f, and that f is v over lambda. So 1 over f must be the same as lambda over v, which means it is valid. Part C, figure 8.1, shows the graph of displacement against time for a wave. Calculate the frequency of the wave as shown. So this is a time graph, so we need a period. The period will come at the end of one cycle. One cycle ends here, or you can count 1.5 cycles if you want, but we've got a nice round number at the end of one cycle here. We just need to identify how much that is. That value there at the end of one cycle is 0.24 milliseconds, and so that's big T, and F is 1 over big T. The milliseconds are 10 to the minus 3, so we need to include that information when we do the 1 over T thing, and that gives us an F of 4167 Hertz. So they're now asking us to sketch a wave which has half the amplitude and a phase difference of 120 from the original wave. So 120 is like a third of a cycle, so 120 degrees over 360 is 1/3 of a period. So that's how much it has to be moved. So it has to have half the amplitude, the exact same wave shape except it's less tall. So it has to have the same period, but it has to be shifted along a third of a period. Now the period is 12 squares long in our graph, so we need a third of that. So we need to shift it 4 squares, which is a third of a period. So we need to come to half of this original amplitude, and we need to have shifted 4 squares along. So 4 squares along is where I'm going to start my wave, and then 4 squares along from the peak is where it's going to reach its maximum, and then 4 squares along from the crossing point is going to be where it will cross again, and then 4 squares along from the next peak is where, oh annoyingly, in here where it will peak again. Maybe I'll just take that off so that we can see what we're doing. I'll just change color for that one. So it's going to be 4 squares from that peak right there. And then it's going to cross again 4 squares. And so that's the kind of shape that we're going to get. So we're going to have something, and it's 3 squares each time it reaches a new phase. So you can see here that 3 squares back is where this would have been peaking. Okay, so the tip here is if you're right-handed, try and draw this backwards, and if you're left-handed, draw it in the forward direction, because your hand will get in the way of where you're trying to see. Something like that. So here we have an optical fiber question. Figure 9.1 shows a section through part of a typical optical fiber. The core is glass fiber that allows light to travel through. The cladding is also made from a transparent material. In practical uses, the fibers themselves are as thin as a human hair, and many of them are bundled together to make a fiber optic cable. Tick a box in 9.1 to show which of the following statements describes the relationship between the index of the cladding and the index of the core. So what are our options? The refractive index of the cladding is larger than the refractive index of the core. Refractive index of the cladding is the same as refractive index of the core. The refractive index of the cladding is smaller than the refractive index of the core. Right, remember, to get total internal reflection, you have to be heading in to a less dense medium, and that means that only the bottom one is correct, because that would mean that the cladding is less dense than the core, and that gives us the total internal reflection, which is the whole basis of how this thing works. Part 2, the angle between the end of the glass fiber and the incident ray is 52 degrees as shown. The refractive index of the core is 1.52. Use these values to calculate the angle of incidence I at the boundary between the core and the cladding. We brought down the bit of the diagram that we're interested in here. So our job is to use Snell's law to find this angle of refraction on the way in, and then use the properties of triangles to find what I must be. They have further complicated it by not giving us I on the way in, which is going to be like 38 degrees. So you need to watch these kind of things. So Snell's law, N equals sine I over sine R. And that means that R would be R would be sine to the minus 1 of sine I over N. So we just pump that through the calculator to get the R value now. Remembering that that is not the answer, because if this is 23.9, then we've got 23.9, then this is going to be 66.1, and that is the answer that we're looking for. Part B1. The shortest time for a ray of light to travel through an optical fiber is when there is axial transmission, so along the center of the fiber, along the axis. That's the shortest distance through. This is when the ray of light enters the optical fiber along the normal. Calculate the shortest time taken for a ray of light to travel through 3 kilometers of this fiber. So we need to use the refractive index to work out the speed of light in the fiber. And the refractive index is the ratio of the velocity in air to the velocity in the fiber. Now the velocity in air is more or less the velocity in a vacuum, but yeah, when they quote n, it's what happens from air to the fiber. So we can get the velocity in the fiber by doing VA over n, and that gives you the V in the fiber to be like 1.97 times 10 to the 8 meters per second. And so now we can use that speed and that distance to get us a time. So converting the 3 kilometers to meters, because the bottom line is in meters per second, otherwise they wouldn't be compatible. So we'll only get seconds out if we've got meters on the top line and meters per second on the bottom line. And that gives us the time for the light to travel through. Calculate the percentage increase in time for a ray travelling through the optical fibre at an angle of incidence at the core cladding boundary of 70 degrees and compared to the shortest time for the light to travel. So that'll be a triangle thing again. So if you imagine it going straight through, that's the short path. Going at this very steep angle, that's the long path. And it will draw this triangle all the way down the fibre. Therefore, the ratio of these two sides of the triangle is going to be the ratio of the whole paths of it travelling down the fibre. So basically, the ratio of long to short here will be the ratio we're after. Now the long is the hypotenuse and the short is opposite to the 70, so we can use the sine. So if we want the long on the top, then we do 1 over the sine of 70 degrees, and that'll give us the value. And that's it. 1.064, which means it's gone 6.4% more than it was before. So that's our increase. And that concludes our business here. Thanks for watching.